Hi everyone. Today we'll take a look at rational functions. So a rational function is any function which can be expressed as a quotient. So in this case, we have a rational function in the form of f of x upon g of x, right? Where g of x does not equal to 0. If g of x is equal to 0, then this entire value becomes undefined because we have any polynomial upon 0, or any polynomial which will result in a constant value for different x's, different values of x, thus resulting in 1 upon 0 form or a constant upon 0 form like this, right? Which will result in an undefined or an infinity form, right? So essentially f of x and g of x are any arbitrary polynomials. We can assume them to be whatever they want, and when they are in this form, they are known as a rational function. So essentially what the IB asks in this small portion is they will ask you to determine the domain and range. So domain, range, and they'll ask you to plot the graph, right? Plot the graph. All right. So before we look at the more example-based questions, let's start with the very basic formula of a rational function. Form of a rational function, which is y is equal to 1 upon x, where f of x is 1, right, and g of x is equal to x, right? That's it. That's our basic form. So if we plot this function, right, basically what I'm going to do is I'm going to plot the function, and then I'm going to tell you how we determine the domain and range of it. Okay, so this function will give you the basic idea of how every single graph is, right? So we have my y and x axes here, right? So like this and like this. So this function kind of looks like this, like this. So if I draw this a little bit more better, if I improve the function, right? You can always go on, softwares like GeoGebra or Desmos, and you can always, or you can use your TI-84. You can plot your curve in here. I'll just do it one more time. You can plot your, you can input the function there, right? So it's like this. So what's happening here is that this function is asymptotic right here with respect to the x-axis and y-axis. It never touches the x and y-axis. Okay, it comes very close to it, but it never touches it. So when this function, when x goes to infinity, right, what you're gonna have is you're gonna have two lines that are very, very close to each other. Like it looks like they're almost touching each other, but they're not. Like the distance is so minute, like you don't even feel the difference. Okay, so now let's learn how to determine the domain and range of this function. So essentially, like I said, this function exists as long as g of x is not equal to 0. So let's look at g of x, right? G of x is technically x, right? So I'll change the color again, and I'll take blue. So g of x is equal to x. So when is g of x ever going to be 0? G of x will be 0 when x is 0, right? So therefore, function is undefined at x equals 0, right? X equals 0, function is undefined, right? F of x, or I can say y is undefined, right? So at whatever values of x, y is undefined. Those are the values that are not part of the domain, okay? So therefore, we can say that domain is domain belongs to x is part of all real numbers, right? All real numbers except, right? Except x does not equal to 0, right? That is our exception here. We can take any value of x except 0. All right, now let's look at the range. How do we find the range? Well, to find the range, there are multiple methods, right? You can take different values and see where it tends to, or whatever, whatnot, all of those things as well. Or what you can do is you can simply just reverse the rules here of y and x. So what I mean is, this time we're going to write the function in terms of y, right? Right now we have it in terms of x, so now we're going to swap the rules of x and y. Okay, so basically we're finding the inverse of the function, and once we find the inverse of the function, we're finding the domain of the function. All right, domain of the inverse of the function. Let me be very clear here. So if we do that, right, If we do that, then I'm going to have x is equal to 1 upon y, right? Now, what is the domain for this function? The domain is quite similar to the one that I've written in blue. It's like domain is, right, y is part of all real numbers except y can't be 0, right? Like this. Right? So y can take any real number except 0. So that is my range actually. That becomes my range. Right? That becomes my range. All right. So what's actually happening here is that this function takes all values. So this will actually slowly, this doesn't look like it's going to decrease, but it's actually just decreasing, and it's gonna almost meet this axis. Similarly, this is going to increase. Sorry. So this is, yeah. So this is going to increase, and it's almost going to meet it. It's not going to touch it. It's never going to touch it, but it's going to be very, very close to it. It's going to be asymptotic, right? That's what it means, all right? So now what happens is this and this, right? All of the exceptions, what these exceptions tell us, or what this exception gives us, is the x and y asymptotes. So this is an asymptote, right? So the line x equal to 0, and so I'll write in a different part, right? So the lines, right? The lines x equals to 0 and y equals to 0 are asymptotes in this function. So in exams, we will always draw them in a dotted format. So the examiner is aware that we are drawing an asymptotic line. So that what it shows is that the function will never touch that line, It will approach that line as x approaches to a certain value. All right. Another way, how we can find the asymptote. Well, another way we can find uh, the y asymptote line, right, as x tends to infinity, is by taking limits, right? If you've already done that in calculus, you can always do that. You can let x tend to infinity, right, and then find the x and y asymptotes, right? You can always do that. But if you haven't learned that, then it's okay. You can always use this method that I've done, and hence find the range of the function, right? So this becomes the range for f of x. So now let's look at a few example questions. So the question says, determine the domain and range of the rational function y is equal to 2 upon 1 minus x, and plot the graph too. All right, so let's start with the domain first, right? So to find the domain, we always let the denominator, right? We always let the denominator equal to 0. So to find the domain, right? So first part is domain. To find the domain, we're going to do 1 minus x is equal to 0. So if we solve for x, we're going to get x is equal to 1. So this is also our asymptote, right? It's our asymptotic line. It's our asymptote. It's our x asymptote, right? It's going to be a vertical line, and we're going to draw a dotted vertical line, right? That's going to be one part. So we can say x belongs to, right? So let me rewrite this. X belongs to all real numbers, but x does not equal 1, right? A value, there will be no output, right? Or y will not take a value when x equals to 1, because the denominator will equal 0, and you can't have a 0 at the denominator, right? So that's simple. Right, now let's look for range. So for range, we're going to reverse x and y, right? We're going to find the inverse of the function. So we have y is equal to 2 upon 1 minus x. Let's solve for x in terms of y, right? So if we do that, I'm going to write y times 1 minus x is equal to 2, right? I'm going to write 1 minus x is equal to 2 upon y. And then I'm going to write 1 minus x is equal to 2, or wait a second. What I can do is I can bring 2 upon y to the left-hand side and this to the right-hand side. So what I get is this is equal to 1 upon 1 minus 2 by y, like this, right? If I want, I can further change the format and write as y minus 2 upon y, like this, right? So now if I find the domain of this function, right? If I look for the domain of this function, y belongs to all real numbers, but y does not equal 0, right? There will be no value for x when y is 0, okay? So that basically is my range, right? So part 2 was range. All right, so now that we have found the domain and range, right, we can also call this the y asymptote, right? So y equal to 0 will be a dotted line, right, as well. So now what we can do is we can start plotting the curve, okay? So I'm going to plot it right here. I'll change the color and bring it white, right? So draw my y-axis, right, like this, this, and I'm going to draw my x-axis like this. All right, so I know I have to draw a dotted line as x equal to 1. So if I take this to be 1, right, I will have a dotted line like this, right, like this, something like this, like this. So I'll draw it like this, and I'll call this as x equal to 1, right? I also have one more dotted line like this, but again, it's going to cover the y-axis altogether. So yeah, now we know that the general curve is something like this, right? Like this or like this, right? Like this. It's going to be something like that. We're not exactly sure what's going to happen, but it's going to be something like that, right? Or it's going to be, if it's like this and like this, it's going to be like this, or I'm going to change the color, and now we're going to put it in yellow as well. So it's going to be like this or like this, right? It's always going to be an opposite. It's going to be like diagonal to each other, right? Either we're going to have the two lines in yellow or the two lines in white, right? We don't know what's going to happen, but it's going to be either one of them, right? So we can expect either one of them. Now, one way we can do that really quickly is just by finding the y-intercept of the curve. So by finding the y-intercept, what I can do is, since x does exist at 0, I can find 0, the y-intercept, right? So if I do that, I'll change the color back to blue, right? I can find the y-intercept. So y is equal to 2 upon 1 minus x, right? So y is equal to 2 upon 1 minus x. I can put, for x equal to 0, 1 minus 0. Y is going to equal to 2. This, right? So if this is maybe 1, this is again 1, and this is 1, 2. So I'm going to have my y-intercept right here, right? And I know that this is my another tangent, right, or my asymptotic line, right? So this is my asymptotic line, this is my asymptotic line, right? It's going to go on like this, right? So now I'm going to have, it's going to start from here. It's going to go very high. It's going to come from positive infinity. It's going to come like this and like this, and it's going to tend to 0 as it goes to minus infinity like this, right? This is the general curve, right? I'm not taking different values like -1, -2, 0, 1, 2, 3, so on and so forth. I can do that, but I don't need to. I'm just drawing a very arbitrary curve, finding the domain and range, and with the asymptotes. So if I know that one's going to be like this, the other has to be diagonal to the asymptotes, right? Forget the axes in this case. Technically our axes becomes the two asymptotic lines. Now, note that we can have more than two asymptotes. We can have 3, 4, 5. That all depends on how complex the function is, right? So we have one like this, and we're gonna have one like this. So it's gonna come like this, or something, just general form like this. Right? It's gonna be like this and like that, and that is how you can essentially draw any rational curve. All right, let's look at a few more examples. All right, graph the following functions and determine its domain and range. So let's look at part A first. Draw a straight line. So right here. So now we can start. So let's start with part A. So we're given y is equal to 1 plus x and 1 minus x, right? Simple. Let's start. Domain and range. So domain, we're going to let the denominator equal to 0. So 1 minus x is equal to 0. X is equal to 1, right? This is our vertical asymptote, right? Vertical asymptote. Again, like I said before, we can have more than one vertical asymptotes and more than one horizontal asymptotes. This is a kind of a fairly simple question. That's why we only have one asymptote, one vertical asymptote, right? And our domain thus becomes x belongs to all real numbers but x does not equal to 1. You can't have 1 in your domain, right? Let's look at range now, right? This is part 1, this is part 2, right? So range, again, what we're going to do is we're going to reverse the roles, right? So when we do that, we're going to have 1 minus x is equal to 1 plus x, right? Open this up, we get 1 minus xy is equal to 1 plus x, right? What I'm gonna do is I'm gonna take this x here, take this 1 here. So I'm gonna get y minus 1 is equal to xy plus x. Okay. Then I'm gonna have y minus 1 is equal to x times y plus 1, right? Y plus 1. Solving for x in terms of y, I get y minus 1 upon y plus 1. So now, if I look at the domain of this function right here, right, I equate y plus 1 is equal to 0, y is equal to minus 1. And this is my horizontal asymptote. Horizontal asymptote. Okay? So, like this. Like this. Okay? That is my second part. So I found, now in my range essentially becomes, range becomes y belongs to all real numbers, but y does not equal minus 1, right? That is my range. So now let's plot the curve, right? So I'll draw the axes right here, right? Like here, right here, and this, like this. Very rough graph. I don't have to be so. It doesn't have to be so detailed. As long as I plot the vertical and horizontal asymptote, show the domain and range clearly, and just show a general direction, nature of the curve. Right, I'm all set to go. Right, so this is my axis. I'm going to change the color just to draw the asymptotes. So my one asymptote is going to be at x equal to 1. So maybe like right here, right? Like right here. So this, like this. That's my asymptote. Okay. And the other is minus 1. So it's going to be like here, here, like this. It's going to be this. So now I'm going to draw my curve with respect to my the green lines or the asymptotes that I've drawn. They kind of become my new axes. Okay. So you can like essentially ignore my purple axes, right? So like I said before, I'm going to have maybe like one line. So either I'm going to have either I'm going to have this or I'm going to have this, right? It's all going to be done with respect to the green dotted lines, right? So again, what I can do is I can just find the y-intercept of the curve, right? So the y-intercept, I can draw it right here, will be y is 1 plus 0 upon 1 minus 0, which will be 1, right? So 0 comma 1 is one of the points. So I'll take blue. So I'll take 0 comma 1, so it's somewhere right here, like this. So that's going to be like, it's going to go this way, like this. And then like this, right? That's going to be the general form of y is equal to 1 plus x upon y is equal to 1 minus x. All right, let's go to the next question. So we have y is equal to minus 1 upon 3 minus 6x. All right, so to find the domain, we're going to let the denominator equal to 0. So we're going to get 3 minus 6x is equal to 0. X is equal to half. That gives me my vertical asymptote, right? Vertical asymptote. And my domain becomes x belongs to all real numbers, but x is not equal to half, right? X is not equal to half, right? That's my first part. Now, to find the range, we're going to just swap x and y. We're going to write x in terms of y. So we're going to have 3 minus 6x is equal to minus 1 upon y, right? Add 3 to both sides. So I'm going to get, what I'm going to get is minus 6x is equal to minus 1 upon y minus 3. Divide by negative 6 on both sides. I'm going to get this is equal to minus 1 upon 6y plus 1 upon half. 1 upon 2, right? 1 by half, right? So now if I look at this, right, the domain here becomes, right, y is equal to 0, right? Because if this is 0, this becomes infinity, right? This is not defined, so not defined plus any constant is still not defined. So this becomes my horizontal asymptote, right? So my range essentially becomes, well, it becomes y belongs to all real numbers, but y does not equal 0. So now let's start plotting our curve. Same way as we did last time. I'll take the same, I'll just draw the axis in the same color. So I'll draw it in white, so that's easier for me to work with. So I'll take white, draw my x-axis, then my y-axis, right? Right, now I'll take yellow, and I'll draw the asymptote. So it's x equal to half. So if this is 1, right? So this is half, right? So, right? And at 0, this, we're going to have something like this, right? So x is equal to half, and y is equal to 0, right? So now, again, either we're going to have a graph that's going to go like this and like this, or we're going to have something that goes going to go like this or like this, right? So to find out what's the general shape's going to be, I can just find the y intercept, right? So if I do that, I'm going to have y is equal to minus 1 upon 3 minus 6 times 0, which is just 0. So it's going to be y upon y negative 1 by 3. So 0 comma negative 1 by 3 is a point, right? So I'll take white again, 0 comma 1 by 3. So, sorry, minus 1 by 3. So it's going to be somewhere around here, right? Where I'll take the original color itself, right? Somewhere here. So my thing is going to be this and like this. Oops, my bad. It's going to be something like this and go down like this, right? Again, it's not going to be so squiggly. It's going to be a straight line, and it's going to, like, tend like this, more like this, right? Similarly, it's going to come like this and go like this, right? That's pretty neat. So yeah, this is how we're going to draw this graph. Final part is y is equal to 3 minus 2x upon 2 minus 3x. All right, let's start with the domain. So domain is when denominator is equal to 0. So 2 minus 3x is 0. So x is equal to 2 by 3. So that's our vertical asymptote, right? Vertical asymptote, right? So our domain becomes x belongs to all real numbers, and x does not equal to 2 by 3, right? Similarly for range, right? We're going to do the same application of what we did before. So for range, we're going to swap the rules of x and y. So we're going to have something like y is equal to 2 minus 3x is equal to 3 minus 2x. 2y is equal to 3xy is equal to 3 minus 2x, right? So we're going to have 2y minus 3 is equal to 3xy minus 2x. 2y minus 3 is equal to x. Let's factor x, so we're going to have 3y minus 2. So x is going to be 2y minus 3 upon 3y minus 2. This. Okay? So now, if I find the domain of this, I can say 3y minus 2 is equal to 0. Y is equal to 2 by 3. So my range is y belongs to all real numbers, but y does not equal to 2 by 3, right? That is my final part. right? So now that I have my domain range and my horizontal and vertical asymptotes, right? I can go ahead and plot the graph with the same approach. What I'm going to do is I can find the y-intercept here as well. If you can't find the y-intercept, right, then you can take any point. You can take x equal to 1, 2, 3, any point which gives you just helps you understand where that one point is be. So you can assume plot out the general form of the curve, right? They're not asking for exact discrete points and exact accurate functions. They just want just a general shape of the entire rational function. Right, horizontal asymptote right here. So asymptote. All right, so if we go ahead and draw this, right? So now let's go back. Let's change the color to line. Draw the axes. Y is equal to 2 by 3 and x is equal to 2 by 3. So I'll just take a general assumption. So something like this: x is equal to 2 by 3, y is equal to 2 by 3, right? So if I take the y-intercept now, right, what I'm going to get is 3 minus 0 upon 2 minus 0. So I'm going to get 3 by 2 or 1.5. So 0 comma 1.5 is a point on this curve, right? So this is 0 comma 1.5. So this is 2 by 3. That's like 0.67. So I can draw like 1.5 is like right somewhere around here. So that gives me the general, direction of the curve. Like this, right? So something like this. And similarly, that's gonna come down here. If I want, I could even find the x-intercept, right? I found the y-intercept, I can even find the x-intercept. The x-intercept, all I have to do is just let y equal to 0. So if I let y equal to 0, if you can do it on your own time, but if y is equal to 0, my x is gonna be 2 comma 3, right? You can just tell by looking, quite evidently, or right? It's gonna be it's not gonna be 2 by 3. It's gonna be 3 by 2, right? So it's gonna be 3 by 2. So it's gonna be like somewhere right here. So like this and like this, like this. I know it's not that great. I'm drawing on a graphic tablet, so it's a little difficult. But you get a general idea of like this and like this, something like like that. So this is the final question, and let's look at a few more out of the box questions. All right, so in this question, we're asked if x is real, the maximum value of the following rational function is what? All right, so if you want, you can pause the video, give it a try. Otherwise, let's get started. So what I'm going to do is I'm not going to do the traditional approach of finding the range, right? Doing what I did before, right? I'm going to be a little smart here. Okay, so what I'm going to do is I'm going to break this function. I can see that this and this is same, right? 3x squared, 9x and 9x is same. The only differing part is this constant, right? So what I'm going to do is I'm going to kind of break this function into two parts. Right? I'm not going to do partial fractions. That's something I'm going to do later. But I'm going to do 3x squared plus 9x plus 10 plus 7 upon 3x squared plus 9x plus 7. So what I did was I just broke it up to match the denominator as well. Or if you want, I can rewrite it this way as well. So I did plus 7 plus 10, right? So now I can, simplify. I get one more way to write it is 3x squared plus 9x plus 7 upon 3x squared plus 9x plus 7 plus 10 upon 3x squared plus 9x plus 7, like this. Right, so this just becomes 1, okay? Now, the remaining part that we just have to work with is 3x squared plus 9x plus 7, right? This is what we need to work with, right? So now our function is actually y is equal to 1 plus all of this, right? So now if I just look at this, right? Now if I just focus on this bottom part right here, right? This one right here, right? If I just focus on that, I'm gonna do something neat here, right? I'm gonna make this a function itself. So I'm gonna write f of x is equal to 3x squared plus 9x plus 7, right? So now if you look at this is an upward facing parabola like this, right? If you remember from the last video that I explained, it's an upward facing parabola. This is going to go to positive infinity and positive infinity. Now remember, the greater the denominator increases, the smaller the total value, right? And the smaller the denominator, the greater the total value, right? So it's kind of an inverse relationship, right, that we have. And we want the maximum value. So to get the maximum value, this is a constant, right? So this isn't going to change. To get the maximum value, we need this to be maximum, right? This needs to be maximized, right? We have to maximize this. And if you want to maximize this, we have to minimize the denominator. Minimize the denominator, right? And the only way we can minimize the denominator is by finding the minimum value. Right, you can do that multiple ways. You can use calculus if you want, find the derivative, find the turning point, whatever. But we can use our simple knowledge that we have from our quadratic function, right? We know that the turning point, right, is at minus b by 2a, right? Minus b by 2a, or, comma, minus d by 4a. Right? We don't really care about where it is on the x-axis, but we care about the y-axis because that's going to give us the value of it. So what we're going to do is we're going to find minus d by 4a, right? So f of x minimum is minus d by 4a, where d is b squared minus 4ac, right? It's a discriminant. So if we simplify this, right, or if we put in the values, we get 81, like 9 squared, right, which is minus 4 times a, 3, and c, right, like this, all upon 4a. So 4 times 3. Simplify this a little bit more. We get minus 81 minus 84 all upon 12. So this is minus 3 by 12, which is minus 1/4. Right? So the smallest value of this function, right, of this function is minus 1/4. Right? So now let me go back to purple. So if I look at if that's the smallest value, right? So y is equal to 1 plus 10, right? I'm going to get minus 1/4, right? Sorry, I meant to put 1/4, not minus 1/4, because this will be negative, but then that'll be outside positive sign. So give me 1/4 only, right? I'm going to 1/4, and then I'm going to simplify this. So this is going to be 41. So the maximum value is going to be 41. Now, one thing I want to point out is, what if this was -4, right? What if this was -4? Then this would be negative, and this would actually decrease. This would be minus 41. In that case, what we're going to do is to maximize this, we're going to take the greatest negative number, or we're going to take the greatest negative number right here, because we want it as small as possible, right? We want this to be as small as possible, right? So we're going to take the greatest negative number, or a better way to let me reiterate. We're going to take the greatest we're going to take the smallest number possible, just in general, right? Because if this is the y-axis, if we got something like this, right, we want to maximize this, right? So we would take basically 0 at that point. We would have taken 0, because we don't want it to be negative, right? We don't want to be negative. If we take a negative, we're gonna get even a smaller answer, because we want to maximize it, right? So again, just be careful of this, because I haven't done multiple questions of these, so you might do this approach. You might put this approach blindly, and then you will realize later that, wait, I was supposed to find the greatest number. So in finding the greatest number, minimizing this function, I found a negative number. Hence, my actual y value was even lower than I imagined it to be. Right? So just be careful of that. You have to take into consideration every single possible case that can occur. Right? So I'll just erase this part, make it a little less messy, so you can take a look at it. All right. So in this question, you have to find the range of the following rational function if x is real. All right, so this is, again, kind of out of the box question. We won't do the exact same approach, right? We're not going to solve So if this is y equal to all of this, we're not going to solve for x in terms of y, then find the domain, because it's going to be very tedious. We have x squared, and we have x and all of that, right? Because then we'd have two values of x's to deal with. You can try it on your own. You're going to find it very tedious. So I'm going to show you another approach that can be used, all right? So let's assume this to be y. Let's use y is equal to 2x squared minus 3x plus 2 all upon 2x squared plus 3x plus 2, right? Now, I am going to take this on the left-hand side. So what I'm going to get is 2yx squared plus 3yx plus 2y is equal to 2x squared minus 3x plus 2. Now, I'm going to get all the x squared together, all the x's together, and all the constants together. So when I do that, what I get is 2y minus 2x squared plus 3y plus 3x, and then I'm going to get plus 2y minus 2 is equal to 0. All right, so now they've said x is real, right? So x is real. That means my discriminant should be greater than or equal to 0. Because for negative discriminants, I'm going to get imaginary values of x, right? Which I don't want. So I'm going to set the discriminant be greater than or equal to 0, right? So that is the approach. We always let discriminant be greater than or equal to 0. So this is like, if I take another color, if I take blue, right? If I take blue, this is A, this is B, and this is C, right? This is a standard approach, right? It's going to work every single time. You don't have to doubt it ever, right? So I'm going to get B squared. So I'm going to get 3y plus 3 whole squared minus 4a times 2y minus 2 whole squared. Because A and C are the same thing, so I'm going to write it like this. Greater than or equal to 0, right? Now I have this, right? So now, how can I simplify this, right? So if you look at this, right? If you look at this very closely, I have something, in the form of, that can be put in the form of a squared minus b squared form, right? But before I do that, I'm going to get rid of this 4, right? I'm going to put this inside. So I can also write this, right? I can write this as 2 squared, right? I can write this as 2 squared. So what I actually have is 2 squared times 2y minus 2 whole squared, which I can write this as 2y minus 2 whole squared. That gives me 4y minus 4, right? So again, my new function, right, is 3y plus 3 whole squared minus 4y minus 4 whole squared is greater than or equal to 0. Right? Now, what I can do is I can expand this and expand this, then I can add and subtract the like terms, then factorize and find the value of y. I can do that. That's not an issue at all. Right? Let's work smart here. Right? Now, if you look at this, this is some term squared minus some term squared. So this is kind of similar like a squared minus b squared, right? So where a is 3y plus 3 and b is 4y minus 4. So if you remember, the factorized form is a plus b times a minus b, right? That will simplify this entire left-hand side with as little as effort as possible, right? That's what I want to do. I want to put the least effort and get the maximum output, which is saving time right here. I'm going to save a lot of time by doing that. So I'm going to go ahead and do that. So when I do that, right, so I'm going to get 3y plus 3, right, plus 4y plus 4, right, times, again, 3y plus 3 minus 4y minus 4, right, greater than or equal to 0. Simplifying this, what I'm going to get is 7y minus 1 times 7 minus y is greater than or equal to 0. Again, so now I'm going to have my critical points, which is y is equal to 1 by 7 and y is equal to 7. These are my critical points, right? So just one change I would like to make here very quickly. What I'm going to do is I'm going to multiply by -1 on both sides. So this is going to be y minus 7 instead of 7 minus y, right? So now what that's going to do is this is going to change the sign as well. So, right. Now I'm not going to explain, how making the inequality, whether it's inside between them or outside them, right? You can figure that out on your own as well. So at the end of the day, the value of y is going to be between, including 1/7 and 7. So that's going to be my range, final range. All right. So that answers the question of how to find the range of this entire rational function. All right. So before we wrap up this video, I'm going to talk about one small thing, which is called oblique asymptotes. All right. So we talked about vertical and horizontal asymptotes. So oblique asymptotes is slightly different, right? So if we have, our normal function as the very basic rational function as y is equal to 1 upon x, right? So that's looks like this, where y is equal to 0 and x is equal to 0 are our horizontal and vertical asymptotes respectively, right? So horizontal asymptote and vertical asymptote. But what is an oblique asymptote? So oblique asymptote is when you have a curve like this, and like this, okay? Something like this. So let me redraw this. So I'll change the color. So something like this and something like this. So in this case, one asymptote is right here, like this, and the other asymptote is kind of like this, right? So one example I'm going to show, right? I'm not going to do too many of this. I'm just going to show one example, right? So one example to find, okay, and there's also a special format in which you can only get oblique asymptotes. So the format which you can get is basically when you have f of x upon g of x, right? And the degree of f of x is one more than the degree of g of x. So when the degree of f of x as a polynomial is exactly 1, right? It can't be 2, it can't be 3, it has to be just 1. Exactly 1 more than g of x, right? So let me erase this. I'm going to make a little bit of space because I'm going to draw the same graph again with the example that I'm giving, a little bit more neater, right? With the example that I'm going to use here, and I'll take pink, right? My example here is y is equal to x squared upon x minus 1. All right. So to draw this graph, obviously it's a rational function, right? So I need to find the horizontal and vertical asymptotes. So let's go ahead and find the horizontal asymptote, which is going to be x equal to 1. It's pretty obvious, right? HA, right? I'm just going to call it HA. Right? HA is going to be x equal to 1, right? My vertical asymptote, right? That's going to be, well, that's going to be like this. So I'm going to do y is x minus 1, x squared like this, right? So now I'm going to write, I'm going to do it like this, right? So I'm going to do xy minus 1 is equal to x squared, right? Again, this isn't really working for me, right? Because if I try to, simplify this a little bit more, I'm going to get x squared minus xy plus 1 is equal to 0, right? I still won't be able to simplify this really well. So what I can do is I'm going to use the previous method, right? I'm going to find the discriminant. So I'm going to do something like b squared minus 4ac, right? So b squared is minus y, so b squared minus 4 times a is 1, c is 1, is greater than or equal to 0. So y squared minus 4 is greater than 0, right? So technically you can think of it like my parabola, right? So y squared minus 4 is greater than 0 when y is greater than 2 or when y is less than 2, right? So that's my range. So my range basically becomes, so there is no asymptote, right? There is no horizontal asymptote, and I would like to correct myself. This is the vertical asymptote, right? So this is the vertical asymptote, and horizontal asymptote does not exist. But I also have my range here, which really doesn't matter. I just care about my asymptotes right now, right? And now, how do I find the oblique asymptote, right? So the oblique asymptote is when I do long division of these two numbers, right? And whatever the divisor is, right? The divisor is the divisor in terms of x is the oblique asymptote. So if I do long division, right? If I do long division of this, right? If I put x here, right, then I'm going to get x squared minus x, right? Subtract this. This will cancel. I'm going to get x here, right? So I can write this function, right? I can write x squared upon x minus 1 as x plus x times x minus 1, right? That's how I can write it. Okay, so this part is my oblique asymptote, right? Oblique asymptote. Or I can say y equal to x is my oblique asymptote at this point, right? So I have my vertical asymptote, I have my horizontal asymptote does not exist, and I have my oblique asymptote, right? So now I'll change the color. I'll draw my axes in white, right? So like this and like this, right? Like this, right? So this, 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 and this, right? So my one of my asymptotes is going to be x equal to 1, right? So it's going to be somewhere like here, right? Dotted lines, right? Like this, right? So to find the oblique asymptote, as I'm drawing, I'll explain this one more time. You have to do long division, right? That is the only way you're going to get the divisor, right? So this is the remainder, right? So this entire portion is my remainder. This is useless. This is useless when I'm finding the oblique asymptote. This could have been x squared plus x, right? So that then well, essentially my you must be thinking it must be x, it could be x squared plus x, but no, it never will be, because like I said, the degree of f of x is exactly 1 more than g of x. So you're always your oblique asymptote will always be some sort of y is equal to kx form, where k is all integers, right? It can be -5, -10, 15, 20, doesn't matter. As long as it's in this form, it's always going to be in this form, right? That is the reason why my degree of f of x is exactly 1 more than exactly 1 more, right? That's the key word, right? So that's my vertical asymptote, right? My horizontal asymptote, my oblique asymptote is going to be y is equal to x. So it's going to be 45-degree angle, right? Something like this. Like this, right? Now here's the question, right? How do we draw the curve? So you can always you can always draw it very blindly, because it's always going to be between the horizontal and vertical asymptotes. So this is my y equal to x, this is my x equal to 1. It's always going to be between these two dotted lines. So it's always going to be the smaller portion like this. Always going to be the acute angle, I would say, not the obtuse angle, but the acute angle, right? So let me just draw one small curve here, and I'll draw the curve in yellow. So it's going to be like this and like this, and then this. Hold on, wait a second. It's going to be like this, right? Again, the range is different, obviously. So it's going to be from y is greater than 2 to y is less than 2. Y is less than -2. I may have made a mistake. I don't think I have, but yes, this is how it's going to pan out to be. So this is oblique asymptote. It's kind of a small portion. It's not there in the Oxford textbook, but I thought I should mention it since I had learned it too. So with this, we wrap up rational functions. Next, coming up, we're going to look at a technique to understand how to solve function questions better. It's called the Wavy curve method. I don't know if your teachers have taught you this or not, but I think it's kind of important, so I'm going to explain that. Then we're going to go with radical functions, absolute value functions, and lots more. All right, so this was all for today's video, and I'll see you in the next one. Bye-bye.